So good afternoon, good morning, good evening, everybody. So we are starting a new IEEE Sequencing System Society Rio Grande do Sul talks. And thank you very much to join us today. So today we have the pleasure here to have a talk by Professor Graziano Pravadelli from University of Verona, Italy. So Professor Graziano, yesterday was elected chair of IFIP Working Group 10.5. So we had no time to update his short CV here. So he has a PhD in computer science. He's a full professor of information processing system at the computer science department of the University of Verona in Italy since 2018. Since July 2017, he is the president of the Quality Assurance Board of the University of Verona. In 2007, he co-founded EDA Lab in Italy, an Italian SME whose mission consists of giving support for the innovation and technology transfer in embedded system modeling and verification. Since 2015, he is also an expert evaluator for UNIVR, that is the Italian agency for research. His main interest focus are on modeling, simulation, and semi-formal verification of hardware and software embedded system, with particular regards to virtual prototyping, correct by construction, embedded software generation, TML, RTL modeling, abstraction application of embedded system to develop virtual coaching platforms for people with special needs. In the private context, he collaborated in several national and European projects, and he published more than 100 papers in international conference and journal, and he's involved also in committees of international conference, like, for example, DATE, DAC, codes ISS, VLSI SOC, and FDL. So thank you very much, Graziano, to accept our invitation. Congratulations again to be the new IFIP Working Group 10.5 that is the main responsible for the VLSI SOC series of conference. And so thank you very much. And now I give you the control again.
Okay, thank you instead for inviting me in this series of webinars. You are doing a great job in inviting many persons. So it is a very interesting series of talks. And I think that you like also my talk today, which is about assertion mining. But before to start, I'd like to thank also my student and the past student that are the main investigator of what I'm presenting today. In particular, Alessandro Danese, Luca Piccolboni, and Samuele Germinani. And first, to start my talk, I'd like also to spend a few minutes in presenting my department. I'm in the Department of Computer Science at the University of Verona, which is one of the largest university in the northeast of Italy. We have 8 degrees among computer science, computer engineering, masters and bachelor, and 9 research areas among computer science, computer engineering, mathematics, and physics. In particular, you can see here the different degrees that we have, and I like to focus your attention on the master degree in computer engineering for robotics and smart industry, because this degree is strictly connected with an important research project that we won from the Italian Ministry of Education, University and Research a couple of years ago. It is a very large project that allowed us to recruit 15 new people, but more importantly, it allowed us to create a new laboratory, the Industrial Computer Engineering Laboratory, that will allow us to explore together with students and industry and companies all the set of enabling technologies for Industry 4.0, from big data analytics to cybersecurity, cloud, simulation, digital twin, etc., etc. We were able to create a real production line. You can see here some picture. We have storage for objects. We have mobile robot. We have collaborative robots. We have equipment for functional testing, quality control, 3D printers, etc. And we can explore all the technologies from the edge to the cloud, both with students and companies. It is really a very nice place for testing new technology, exploring idea, and creating also a digital twin with respect to the industrial field. In the advisory board of our laboratory, there are also Professor San Giovanni Vincentelli, that you know very well, and also Professor Samarjit Chakrabarti from Chepelil University. It is a great opportunity open for cooperation also with all of you, and in general with industry and companies in Italy and outside Italy. In this context, I focus my research, which are the one reported by Riccardo during the introduction. Historically, I started with some fault simulation during my PhD. Then I enlarged my vision towards the virtual prototyping to exploit, in particular, technologies related to the verification, and more specifically on assertion-based verification, where I'm working on the generation of assertion and also the analysis of the quality of this assertion. And as said by Riccardo, more recently I focus also on ambient assisted living to develop a virtual coaching system that exploit the embedded system for improving the quality of life of people with special needs, and in particular with neurodegenerative disease, like, for example, the Parkinson, where we worked, for example, to develop a system that allow this person avoiding the effect of one of the most disabling symptoms of Parkinson, which is the freezing of the gait. But today I will focus on verification, talking about assertion mining. So we will see what is the context, what is assertion mining, how we can do assertion mining, and where we can use the outcome of this procedure. So let us introduce the context, which is the one of assertion-based verification. Of course, when you have to verify a design, you need to combine three different visions. You have the design intent, which is generally from your customer, the design specification, which is the attempt of capturing in a formal way the intent of the customer, and the design implementation, which is the final result of all the process. And these three bubbles must match the same intent, of course. And the role of verification is so to analyze the informal specification to see if the final implementation meet the assertion that are formalized. Generally, in a company, we have two different group of people, one that start from the informal specification and that implement the design, and another group of people that formalize the informal specification in some formulas. We can call assertion, properties, formulas as we want, but the idea is to have a formal language to capture the intent of our customer. And then, of course, the verification matches the assertion with the design. The problem is that defining this assertion in a manual way could be very difficult because the design intent is generally ambiguous. Okay, and it is difficult to talk with customer to identify exactly what is their intent. To do this, we can have the support from assertion, from temporal assertion, which are mainly divided in three different categories. We can have, first of all, invariants. An invariant is like something that never changes, like, for example, the Dolomites, which are very famous mountain near Verona, or the Roman amphitheater we have in our city, whose name is L'Arena. Invariant are formula like grant 1 and grant 2 are never both high. But of course, we can have also sequences of events. As you know, in Italy, we have different dishes when we are at dinner or at lunch. So we start with the appetizer, then we have spaghetti, and then meat or fish, and finally the dessert, and of course the cafe. So this means that we have to follow a specific sequence of behavior, which can be, for example, if a requirement is raised in one cycle, then a grant must be high in the next cycle, and another grant, and the grant must be low in the next cycle after that. And finally, the third kind of assertion we can have are eventualities. Eventualities means that if you go for ice skating, you can fall down. So eventualities are formula like any request will be granted eventually, or no grant until a request. So independently from the kind of assertion that you are defining, invariants, sequences, or eventualities, at the end, you need a method to check if your assertions are satisfied by the design, and you have two different paths, the formal one and the dynamic one. In the formal case, after the initial specification of the design, you need to translate the design into a model, which is generally state transition graph or a labeled model, where you use a decision procedure that mathematically and rigorously try to analyze the model to see if it meets the assertion you define. Of course, this is exhaustive as an analysis, and at the end you will have an answer which is true and false if you are lucky, because in some cases, if the computational resources that this decision procedure needs to complete an analysis is too high, you can have no answer. Okay, so you have an abort of the procedure because the state explodes, etc. On the other side, you can have dynamic assertion-based verification, where the initial design is not changed. You do not need to encode your design in formal models, but you need to transform the assertion in something that can be simulated. And in this case, you will have a design which is composed of your C, C++, HDL-based implementation, plus the checkers that will analyze the execution of the design according to a set of stimuli that you provide to your system to answer with true or false. In this case, you are very fast. You will not have no answer. But the analysis could be not exhaustive because it depends from the quality of the stimuli. Low quality stimuli will mean a not trustable verification. Very high quality stimuli probably will provide a very high quality verification. The problem in both the cases, even the case of formal verification as well as the dynamic verification, is the assertion definition. This is a very time-consuming step that requires high expertise, which are not generally present in companies, especially if they are small companies. But these small companies are the ones that have the most important problem in discussing with the customer about the specification. Okay, and so at the end, the definition of assertion can terminate with an incomplete, wrong, or a redundant set of assertions, making very precarious and uselessly long the assertion-based verification process. In this context, assertion mining can have a role. What is assertion mining? It is the procedure of automatically generating assertion starting from the implementation and in particular from the design under verification, from the source code of the design, or from the simulation traces related to such a design, such that the verification engineer do not need to waste time in manually defining assertion. And in particular, if you extract this behavior, if you infer your assertion from the simulation traces, we can talk about dynamic assertion mining, which is the focus of my talk today. So as I already saw, the verification procedure is the one reported in this slide, but when you do assertion mining, something changes. In particular, the verification, the formalization of the assertion disappears, and a new process appears. From the informal specification after the implementation of your design, the simulation allows you to extract execution traces that show the value of your primary input and primary output per each simulation instant. And from these execution traces, a procedure can be applied to automatically extract assertion. If you do this, of course, this assertion represents exactly the behavior that you implemented in your design. But now the verification must move from this position between assertion and design to this new position between assertion and informal specification. Because now the question is not, are the assertions satisfied by the design? But the question becomes, are the assertions consistent with your informal specification? This kind of assertion can allow you to understand if you implement, for example, something that are not included in that is not included in the initial informal specification. If some unexpected behavior has been implemented, or if some expected behavior has not been implemented because you cannot find any assertion that describes this expected behavior. So this is the idea of assertion mining. But how can we extract such assertion? If we look at the state of the art, we can see that there are many approaches in the field of RTL, TLM, embedded software and software protocol level, and also approaches that work at the Boolean and not Boolean level. I mean, that are able to work with Boolean variable and also with more complex data type, like, for example, integers. At the very beginning, one of the most famous paper was the one by Ammons, which in 2002 proposed a way to extract specification from software. The works in the software area were mainly devoted to the extraction of protocols, to verify the protocols, to verify if the sequence of procedure call was correct. While 10 years later, an inspiring work by Professor Sesha proposed a way to extract assertion for the hardware domain, and in particular to extract assertion from simulation traces at RTL. And then other group investigated this possibility. Another famous tool has been developed by Professor Vasudevan with her gold mine approach. Gold mine is very used in our area. The problem is that all of this works on the Boolean level. If you want to predicate by using integer, for example, or more complex data type, the only solution at the time we started our analysis was the DICOM tool by Professor Ernst, which is a very effective and efficient invariant miner. So it is able only to extract invariant that are formula throughout the execution trace, but it is not able to predicate about behavior, temporal behavior. So you can see that we have here some hole in the state of the art, and in particular some open issues. The tools and the methodologies that are in the literature generally create a too much, too long, too complex set of non-human readable assertions. And this is a problem because I started saying assertion mining allows you to extract assertion, and then you can look at them to understand if you correctly implemented your design. But if these assertions are not readable, they cannot be used for this purpose, but they can only be used, for example, for automatic verification, etc., and so on and so forth. Secondly, this tool generally predicates almost on all the primary input and primary output of your design, and generally mixes they mix the control signal with data signal, making more complex the assertion. And finally, they are able to extract assertion for a set of predefined templates. But if you want to explore other alternatives, you cannot do this. At the end, the result of these tools, which is anyway very, very interesting, can be also over-constraints. So you obtain a set of over-constraint assertion, which cover only a part of the behavior of your design. And then that are impractical for an analysis that want to understand if all of your behavior have been correctly implemented, because you generate a lot of assertion, and without any ranking procedure, you cannot focus on the most important assertion. So coming back to the state of the art, it is clear that we wanted to fill in the gap. And so we started in 2015 to define a tool whose name was Oden. The name derived from the fact that Oden is a Japanese dish that use in the ingredients the daikon radix. And daikon is the name of the tool by Professor Ernst. In fact, our Oden tool exploit daikon by Professor Ernst to generate the invariant as basic block of more complex assertions, temporal assertions. Then we discovered that the most time-consuming part of our approach was indeed the extraction of the invariant by using daikon. So this was the real bottleneck of our approach. It is not a problem of daikon, but a problem of how we use daikon inside our tool. And so we have the necessity of improving this part. So we move from one radix, the daikon, to multiple radix, the mangrove. Okay, and we developed a tool whose name is mangrove that you can download freely. At the end of my presentation, you will have the repository for the downloading this tool, which exploits GPU for generating invariants. And all of these are the basic block for the final tool, whose name is A-Team. A-Team is a famous TV series of the 80s, but it became also the name of our automatic generator of assertion, where we replaced the original character with the faces of our team. And we added one more because in the A-Team there were 4 characters, but now we are in 5 in our group, or 5 that are the person that worked in the time to the development of A-Team. So what is A-Team and how does it work? As said, the basic block is an invariant, which is a formula, as said before, that holds on a specific instant during the execution of the design. For example, let us consider this simple code, and this is A greater than B is an invariant, which is true each time you run this code, you execute this code. Of course, invariant by themselves can be used for documentation, for bug identification, and in many testing and verification approaches, but they don't predicate over the time. So they are not able to capture temporal behavior. To capture temporal behavior, you need a temporal logic, like, for example, LTL, linear temporal logic, where the most important operator are the one reported in this slide. So the next operator, which means that if A is true now, then B must be true in the next simulation instant. The until operator that describes a behavior that can happen in the future. And so in this case, A must be true till first or later B will be true in the future. The release, which is in some sense the dual of the until, the always, that means that your requirement must be true throughout the execution of your design, and the eventuality that allow you to predicate or saying first of later something very good must happen in my design. And with this operator you can define liveness assertion or safety assertion. A safety assertion is something that says you cannot have something bad. You cannot have something bad in any instant. And the eventual operator, the liveness property, is instead first of later or later you will have something very good. So our A team is able to extract linear time logic temporal assertion by using the operator that I presented in the previous slide, with a procedure that is composed of three main steps. The first is the extraction of proposition. A proposition is an invariant, okay? So the invariant is extracted by providing a set of templates. The user can set his or her own template, and then the tool searches for instances of such template that replace the placeholder from the template with actual values, actual variables included in your design. And then we have an a priori algorithm, a priori based algorithm that try to compose the different proposition, atomic proposition, into more complex proposition. So by combining the most frequent proposition, we can have more complex proposition. At that point, this complex proposition became the ingredient of the assertion miner, where a set of justification rules try to compose different proposition into temporal assertion, like, for example, the one reported here on the right of the slide. At the end, we have an evaluation procedure that tries to preserve the assertion that increases some sort of assertion coverage and that discards the one that are not adding anything more to our set of assertion. In this way, we can have a minimal set of assertion that try to describe, to capture all the behavior implemented by the designers. Going more into detail, the proposition miner starts from an execution trace. As you can see here, we have the time and the value of the different variable per each instance of time. The instance of time depends on the granularity that you want to use. It could be clock cycle, it could be transition based, it could be the main loop of a software execution, it can be whatever you want, okay? And then we create the cone of influence by putting together the variables that are related and excluding the other. And finally, by using Mangrove or Daikon, we extract the basic block that are the invariants. Okay, and we compose them into a set of item set that are ordered according to their frequency in the execution trace to extract the list of the final set of atomic of proposition to be used in the next step according to the support. That is to say, according to the number of time that, for example, V1 is true in this execution trace, that the more complex proposition V3 equal V4 and V1 is true in this execution trace, etc., etc. At the end, these propositions are provided to the assertion miner that will try to instantiate temporal assertion in the form always an antecedent imply a consequent, where the antecedent and the consequent can use the temporal operator with the only restriction that the antecedent can use only the next operator and it cannot use the until and the release. But this is generally also what a human does, okay? Probably, very likely, the until, the release, the eventually are in the consequent, while the antecedent is just a chain of next. And through a set of inductive formula, inductive procedure, we compose and create the assertion. For example, let us consider the execution trace on the left, and let us consider that the user asks the miner to generate all the assertions that respect this template, where P1, P2, and P3 are placeholders that must be substituted by actual proposition. So we create the syntax tree, and we start by substituting the leaves with the proposition extracted in the previous step. So for example, we can substitute P2 with V3 equal 3. The next step will try to identify what we can put in place of P3. And so we see in the trace where V3 equal 3 is true, and we analyze what happened in the next step, because until requires something that will start to hold when this part on the left of the until will stop to hold. And so in this case, we collect the proposition and we substitute the P3 placeholder with some formulas, and then we go back on the trees by justifying the implication, which means looking what is true when exactly V3 equal 3 is true, because the implication says P1 imply that this is true until, okay? And in our case, we see that this formula is true together with V3. At this point, we have to remove some inconsistencies. For example, we discover that it is not true that each time V1 and V2 equal 0, 0, 1, we have also V3 equal 3. In fact, at simulation instant 1, V3 equal 4. So we have to remove this part of the antecedent, and consequently, this forced us to remove also part of the consequent, because this is not true when we remove this part in the antecedent. And at the end, we obtain our assertion as reported on the top of this slide. At the end, to make the evaluation and minimize the set of assertion, we use an assertion coverage matrix that relies on fault injection, fault simulation. So we put some mutants, some faults according to a fault model into the design, and then we try to analyze which assertion are able to cover which faults. That is to say, which assertion became false in presence of which faults. Because in this way, we can create our assertion coverage, which is the number of faults causing a failure in an assertion with respect to the total number of faults injected into the design. And by combining the assertion coverage per each assertion, we achieve the total assertion coverage. In this way, we can identify that one assertion is covering the blue part of the behavior, another the red part, another this part, and so on and so forth. And at the end, we can also apply some heuristics to remove some assertion that cover a behavior already covered by others. So we remove this and we remove this to minimize our set of assertions. And this is the result of our A-team procedure. We have here some experimental result where we compare A-team with respect to gold mine. What we can observe is that generally A-team generates a lower number of assertions with respect to gold mine. Concerning the size of the assertion, the antecedent of the formula is generally smaller, which means that it has a lower number of variables, and the assertion that we extract have generally a higher assertion coverage with the one extracted by gold mine. But on the other side, we have execution times that are higher, one order, in some cases 2 orders of magnitude higher with respect to gold mine, due to the fact that our procedure analyze several templates and not only a predefined set of templates for extracting assertions. At this point, independently from the fact that you have gold mine, A-team, or other tool for assertion mining, the question is, where can we use the assertion extracted from these tools? And the idea is that these assertions are very useful in the context of virtual prototyping, because in the context of virtual prototyping, you want to parallelize the development of software with respect to the development of hardware, you start with the initial set of specification. You create an initial system architecture to map in the different parts, and then you generate an executable system specification, such that the software engineer can configure and test their software while the hardware designer produces the hardware component. So in this case, you can save a lot of time during the procedure to finally obtain the silicon hardware prototype and the embedded system software already developed without waiting for the time when the hardware board will be ready to be tested. So in this scenario, assertion-based verification, and in general, the assertion that you can manually define, but for sure, even more automatically generate, we can improve the functional verification by several ways. First of all, this assertion can allow us to discover unexpected behavior, that is to say bugs, or to prove that desired behavior are actually implemented in your virtual prototyping. And in general, given the fact that your virtual prototype will be changed several times from abstraction level to abstraction level, by adding new IP core, by removing one, by changing some behavior, etc., you can reuse the assertion that you generated to verify the design at different abstraction level, to check future evolution of the same design where you are adding some new feature or you are changing some feature, to port an IP into a larger design together with its own set of assertions, and in general for many other verification activities. Also, to do some extra functional verification. And this is the last part of my talk, where I will show you how assertion mining can be used also for generating power state machine. So what is a power state machine? It is a very well-known model that allows you to describe how an IP behave with respect to the power consumption. So it is a state machine where in the state you can see how much power is consumed by the design when it is in the off, in the idle, in the run, and in many other states according to your model. What is the problem? The power state machines are a very useful tool to make exploration and to evaluate different power management solutions, but they are generally defined manually by looking at the datasheet of the component of your system, which at the end became a simplified model with a low level of accuracy. On the contrary, we would like to automatically generate more accurate power state machine. So the idea is to have an IP functional model that you want to integrate in your virtual prototype, and you want also to integrate a power state machine to characterize also extra functional properties of your system. You can generate this automatically by following this procedure. First, you extract some functional traces by functional simulation. Then you can exploit some gate level power simulator to extract the power traces. A power trace allows you to understand the power consumption per each simulation instant with respect to the functional trace that you simulated. It is very precise, but you can run this kind of simulator only when you have the gate level model. And of course, it is very slow. Okay, so if you think that you want to import an IP into your virtual prototyping, which is a very fast model, you cannot bring into this prototype a gate level simulation. But you can exploit the power traces generated once by the power simulator at gate level to create a system level view of your power state machine. In which way? By mining the IP behavior, that is to say, by extracting assertions to represent, to capture the behavior of your design. And according to the fact that similar behavior will have similar power consumption, you can create the state and the transition of a power state machine. Then you can combine different power state machine according to different power traces and to different functional traces, and optimize them to achieve a final model, which unfortunately can be in some cases not deterministic. And for this reason, we implemented a System C version that exploits hidden Markov model to solve the non-determinism of this power state machine and to try to reduce the error that we can have with respect to the original gate level power simulation. Going into the details, the tool works as it follows. So again, we have a functional trace, and again, we do mining of proposition. This proposition create a proposition trace that are proposition true per each simulation instance. If you look at the proposition that are extracted, you will see mainly two behaviors. Your system will jump from a behavior to another for a while, and then it will reach a stable condition, and it will stay in this stable condition for a while till another chain of steps will be made. These two kinds of behavior can be captured by these two patterns, P implied next Q and P until Q, which are the only two templates necessary for generating a power state machine. In which way? By analyzing when the first pattern or the second are true in the proposition trace. For example, here we can see that PA is true from 0 to 3 when PB start holding. Then we can collect from the corresponding power trace the value of the power consumption. And we create one state that says from time 0 to time 2, our system has a power behavior which is the average, the mean of these values, which indeed are very similar because a functional behavior will have probably the same power consumption. In the cases this is not true, of course we cannot compute just the mean of this value, but a more sophisticated regression, linear regression approach must be adopted to generate, instead of a constant here, a more complex function. And this is generally true for the cases in which the model is, the power model is data dependent or time dependent. While in the case it is behavior dependent, you just need the mean value of the power trace. And you can go on in this way by collecting different states and by joining them according to the assertion that represent the behavior in the functional trace. This approach allows you to create one power state machine per each trace that you simulate. And the power state machine is just a chain of states. But then we can compose all of them in an integrated power state machine with two procedures. One that tries to simplify states in the same trace, which are very similar from the point of view of the power consumption. For example, merging B with C and G with H. And then by also merging states belonging to different traces, but that again, according to some statistical tests, have the same behavior from the power point of view. At the end, what we obtain is a power state machine composed of different states, only one integrated power state machine, which can be, in some cases, not deterministic. In particular, when merging states, you can reach the situation where a state has two or more outgoing transitions labeled with the same assertions that act as guards. In these cases, you cannot choose deterministically which edge to traverse, and the hidden Markov model does the work to decide in the best way. As experimental result, I can show you in particular the saving in time. The first column show the second, the prime time column, show the second for simulating 500,000 instances with prime time, which is a commercial power simulator by Synopsys. And if we compare this with the last but one column, which is the time required for simulating the power traces by using the power state machine that we generated in System C, you can see that you can save a couple of order of magnitude, which is very important when you are going to introduce your IP with the power state machine in a virtual prototype. The last column shows the mean error, the error introduced by the fact that we are not deterministics, and by the fact that it could be that your simulation traces are not complete. So in the case you at a certain point reaches a behavior which has not been simulated with your initial set of traces, the power state machine does not know where to jump. So in this case, the hidden Markov model made some assumption and jumped to the most promising state. This caused some error. In conclusion, I proposed and presented some works related to assertion mining, in particular automatic generation of assertion, both by considering invariant and temporal behavior. And I said that this is very important when you want to create your virtual prototype, integrating the functional part, but also the extra functional part. There are many application fields where you can use assertion mining, which is for sure assertion-based verification, but also stimuli generation, power state machine generation, and many other. And we are currently works in particular on exploiting assertion-based verification and in specifically the assertion mining for the analysis of vulnerabilities in the firmware, for Trojan detection, and other aspects related to the embedded security. And that's all. So thank you very much for your attention. Here you can see a list of selected publications. In some cases, there are also the link to the tools that are freely available. In particular, I can say something about the MIST tool that will be presented next week during the VLSI SOC conference, because this is a tool actually used by a company. The problem of this company was that it is difficult for them to discuss with the customer to make an agreement on the intent, on the design intent. And so they asked us to develop a tool to simplify this procedure. It takes 6 months of development, and at the end we had a 2-day workshop with the company last week to train them on the use of this tool, and now they are using the tool for a new project. And according to the first impression, they are very happy to use such kind of tool because it simplifies the definition of assertion, the synthesis of the monitor and the checker, and it is totally integrated in their commercial virtual prototyping simulator. So I invite you to download this tool and provide also your comments on the use. Thank you.
Thank you very much, Graziano. So we have one question by Valmor Cordeiro from Dreamship Technologies in Eindhoven, Netherlands. It seems that the quality of the stimulus is still the bottleneck of this approach. if the stimulus is not good, I will get a set of inconclusive assertions, right?
Yeah, thank you very much for this question. Indeed, Valmor pointed the main problem of assertion mining. Of course, if the quality of the initial stimulus is not good, the assertion that you generate is a partial set. However, we have to say that when you arrive at the point of generating assertion, probably you passed several other analyses. You developed test benches, you did some unit integration testing, you already had the possibility of creating a valuable set of stimuli. If this is not the case, the problem, in my vision, is not of assertion mining, is on the test bench. So first, you have to create your own test bench, you trust them, and then, of course, you can apply assertion mining.
Thank you. So now I have a question for you. So can you talk a little bit about the running time of all this?
Okay, so the running time of the assertion miner depends on two main points. Depends on the number of templates that you provide to the tool, because you can provide your own templates. Okay, so if you provide a lot of template, then you will have much work to do. And the other point is how many simulation traces you are going to provide. So longer is the simulation trace, longer will be the execution time. But fortunately, it does not depend, the execution time, it does not depend from the complexity of the design. I mean, from the code, from the implementation code, from the size of the code, and from the complexity inside the design, because it just relies on the simulation traces.
Okay. So I still have another question. Do you consider also the options related to have more or less power consumption and so on?
Can you repeat the question?
Do you consider also in the process if the solution will have more or less power consumption?
Power consumption has been, I'm not sure to catch your question, but power consumption has been analyzed in the context of the generation of the power state machine. Okay, so we exploited assertion mining for creating a model that allowed to estimate the power consumption of the design. Is it what you are intending? Or?
Yes, this was, and I have another question related, is that the estimation of the power is based on what? Because finally the power will depends a lot on how is going to be the implementation in lower level.
Yeah.
If there is optimization of gates and so on, and now the static power is becoming more and more important and then more complicated to estimate.
Yeah. So the power state machine are intended to analyze the dynamic part of the power consumption related to the switching activity, mainly related to the switching activity. And our power state machine relies on the traces generated by a gate level power simulator, where you can do all the optimization that you want, etc., etc. The main point is you want to integrate a model into a virtual prototype. So probably you already have a component, maybe also at gate level, but you want to integrate with other one, with new one, and so you don't want to reuse a so slow power simulation at gate level, but you want to have a TLM model, for example, of your design. So in this case, extracting the behavior of your precise power simulation at gate level and porting it to the TLM is a way for speeding up the simulation in the context of the virtual prototype.
So we have another question by Kitan Mohammed. So are the assertion mining could be used for safety and security verification?
In general, we apply assertion mining for extracting the behavior. We are exploring now the idea of using this for analyzing vulnerabilities, so going towards security, in the context in which when we find a vulnerability, a security issue, we can identify the problem, but we don't know what is the cause. And in this case, assertion mining can allow us to identify the cause of a vulnerability. Where is the problem? We can identify the location where the problem originates to simplify the phase of the patching. Okay. In this sense, assertion mining can be used also for security verification.
So thank you again, everybody, to attend this session. Thank you again, all the attendees that were here today. And mainly thank you again, Graziano, for this very nice and inspiring talk in a very important subject. So
thank you to you. Thank you to you again for this opportunity.